Hey everybody, it's Mr. N here again, and this is the 10.4 lesson, for our Big Ideas book, and this is on inscribed angles and some polygons. And let's start with what an inscribed angle is. Right here is our inscribed angle, and it's an angle whose vertex is on a circle and whose sides contain chords of the circle. In other words, this vertex right there has to be on the circle, and then you form your angle inside that circle. So as long as the vertex is on. Remember, we did a central angle where it was the center and we made the angle, but now this is an inscribed angle where the vertex is on the circle. What happens is the angle will intercept the arcs. So this angle right here, that would be the intercepted arc. So the intercepted arc consists of endpoints that lie on the sides of an inscribed angle and all the points of the circle in between them. A chord of the arc subtends an angle if its endpoints lie on the sides of the angle. So if we take a look here, you can see here's our inscribed angle. This blue one is the intercepted arc. Angle B, we say this angle B, intercepts arc AC, so that's our intercepted arc from our inscribed angle. And then AC, this arc AC subtends angle B, and this segment A to C, the chord, subtends angle B. So that's the terminology there, subtends the angle. So the intercepted arc subtends the angle, the chord subtends the angle. All right, let's move on to the next thing. What is the relationship that we can form with these inscribed angles? Well, remember, when we had a central angle, and let me draw a circle for you here. When we had a central angle and we did this central angle had the same angle value as the arc. So if this was 40 degrees, this arc would be 40 degrees. Well, something different happens with an inscribed angle. With an inscribed angle, this angle will be 1/2 the whole arc. Notice it can't be the same because you're moving it out further. So it can't be the same as this because you're moving it out further. And so you're changing, kind of like, think of it, this angle by pushing this vertex way out to here. It's changing the angle. So what ends up happening, though, is it's going to be half the intercepted arc. So angle D is equal to 1/2 arc AB. And if you really want to see a proof of this, it's on page 560 of your textbook. But if you were going to prove it, you need 3 different cases. You need the case where, suppose this inscribed angle was, you had a diameter where it went through like this. Then we have case 2, which is just a regular inscribed angle. And case 3, notice how it's on the top, or you could say if we did it down here at the bottom, but it's outside, the center is outside the inscribed angle. The center is on the inside of the inscribed angle, and the center is on. So there's 3 different cases. You have to prove all 3, and all 3 are a little bit different. Just to give you an idea, like for this one, so like in case 1, say, we have this situation. We could do case 1 and use case 1 to prove case 2 and case 3. But we have to prove case 1 first. And what you could do is something like this, where suppose I did that little deal right there and create another radii. These 2 would be congruent. These angles would be congruent by the isosceles triangle theorem. And then you can, at this point, say that this exterior right here would be the sum of these 2 remote interiors. So we're using a bunch of things that we've already learned. And because this is the sum of these 2, and these 2 are the same, then that means this is half what that would be because these 2 are the same. Does that make sense? Kind of. But anyway, after you do that, you could prove these 2. Here's a corollary to all this. If inscribed angles of a circle intercept the same arc or subtend to the same chord of an arc, then the angles are congruent. This is what this is saying. Notice if I drew in here, and let me highlight it here, see this arc A to B. Notice this angle, the red one, this red inscribed angle has the same arc. The blue inscribed angle has the same arc. The green inscribed angle has the same arc. And they're all going to be half of these. So if these intercept the same arc, then they're all going to be congruent. And that's what that's saying right in here. So because it's going to be half of those. All right, moving on. If I put, let me see if I can erase this. I know this is kind of getting stuck here. So let's see if I can somehow erase these. Okay, there we go. In an inscribed polygon. So if I have an inscribed polygon, that just means I'm going to draw the polygon inside the circle, and notice all the vertices will be on the circle. So a polygon is an inscribed polygon when all the vertices lie on the circle. We could say that this circle is circumscribed about the polygon. And then we have the inscribed right triangle theorem. Now, again, you know how I feel about this with your book and your author. This it needs to go. He needs to give credit to who came up with this. This is Thales' theorem. Okay, so this is Thales' theorem, and we really need to give credit to where credit's due. We can't just take credit for it ourselves. Thales discovered this, and basically, here's what he said. I mean, and this was like in 600 BC, and he said, if you have 3 points on a circle, and this is a special case of the inscribed angle theorem, if you've got 3 points on the circle, and you connect this, and this happens to be a diameter, so I connect A and C and it happens to be a diameter, then angle B over here will always be a right angle. Now, this is really cool to show. If I was in class, I could pull it up from other websites, and you can do it yourself by just looking up Thales' theorem, and you can drag this point along, and you'll always see that this stays as a right angle. So it's pretty cool. There's some graphics. You just drag point B along, and you'll see that this always stays as a right angle no matter where I put it. So for example, I can just go ahead and put point B right here, and let's do this in this color. Put point B right there, and I draw that, and that's going to be the right angle again. So I can't show you that here on this software. It doesn't let me import any other type of graphics like that, but it's pretty cool. So anyway, that's a special case of the inscribed angle theorem. If it's a diameter, if this chord happens to be a diameter, you'll always get a right angle there. And then we've got the next one, which is the inscribed quadrilateral theorem. If I put a quadrilateral inside a circle, so if I inscribe it in a circle, if and only if its opposite angles will be supplementary. So a quadrilateral can be inscribed if and only if its opposite angles are supplementary. So these are the opposite angles, E and G. Those would have to be supplementary. F and D, those would also have to be supplementary. So E and G would add up to be 180. F and D would also have to add up to be 180. And then finally, this goes along with the inscribed angles. All these kind of go along with the inscribed angles. The measure of an angle formed by a chord and a tangent is equal to half the measure of the intercepted arc. We're going to talk about this in the next section as well, but since we're talking about inscribed angles, here we go. So if this happened to be a tangent, so you see you still kind of have an inscribed, it's not so much an inscribed angle, but you have this intercepted arc. This will be half that, just like we did it with the inscribed angles. So it kind of goes along with that. All right, you can look at the construction on page 557 of your book, How to Construct a Square in a Circle. They actually do a pretty good job, so I'll just let you reference that. And let's go ahead and look at our student journal, and we're going to do page 197, 1 through 7. All right, so here we go with our first example on that page. And let's take a look at it. It says, in 1 through 5, use a diagram to find the indicated measure. Okay, so we have a diameter here. We're given BC as a diameter. We've got 2 other chords. So right away, since I know that this is a diameter and I'm drawing this triangle inside of here, Thales' theorem tells me that that's going to be a right angle. So we can find the measure of angle A, and that's 90 degrees. The measure of angle C, well, if that's 90 and that's 28, then angle C is going to be 90 minus the 28, which would be 62 degrees. All right, moving on to the next one, number 3, BC. B to C, we want to find that length. Well, if this is 7.3 and this is 3.9, we know that BC will end up being the square root of 7.3 squared plus 3.9 squared. And I can go through and solve for that. And putting that into my calculator, 7.3 squared plus 3.9 squared, and take the square root of that answer, that gives me 68.5, and take the square root of that, I will get 8.276 for the length of BC. Okay, now we're looking for the measure of arc AC. So this arc right in here, AC. Well, if this is 28, this will be double that. So that's going to be 56 degrees. And then we need to find the measure of arc AB. So the measure of arc AB, which is this one right here on this side. Let's go ahead and use a different color on that. We'll go back to a blue here. So we're looking for this one from arc A to B. And here's the trick to this. I just found that AC is 56 degrees. I know that all the way like this will be 180. So we could say 180 minus that 56 is what arc AB is going to be, which would give me 124 degrees. Okay, let's see what we have in the next question. Name a pair of congruent angles. Well, if we can find an intercepted arc, then that's the same. Take a look here. Oops, I don't know what I did. But if I'm looking at arc AD right there, this angle is going to be half that, right? But then this angle will also be half that because that's the same thing. So angle B is congruent to angle C in this case. So that's one pair. Okay, let's erase that and take a look and see if we can find a second pair. So I'm going to erase this, and let's see what we can look and see to find here. So if I take a look at this, well, take a look at angle A. Angle A is made up of arc B to C, and so is angle D. Angle D here, it has the same intercepted arc. So since it has the same intercepted arc, the angles are congruent. Angle A would be congruent to angle D. So that's the second one. All right, let's take a look at the next question. This is the last one here. And it says, find the value of each variable. Well, we know that this quadrilateral inside will add up to be 360, obviously, but we also know the theorem where these angles are supplementary. And that means m plus 65 will have to be 180, and n plus the 100 would also have to be 180. So that means subtract 65 from each side. M would have to be 115 degrees. And n over here would have to be 80 degrees. So those examples were pretty quick, pretty simple. You can obviously dive deeper into this, and you will be doing that in your homework. So hopefully this lesson made sense and inscribed angles weren't too hard for you. So thanks for watching. Make sure you hit that like button, subscribe, and see you in the next video.